Good morning, everyone. I am Mansur Basha from RGUKT RK Valley. As part of my Embedded System online internship at Emertxe Technologies, Bangalore, I developed an EV ADAS dashboard using STM32 Blue Pill, PicsimLab, and a Python dashboard. This project demonstrates how embedded systems can be used for real-time electric vehicle monitoring and advanced driver assistance system or ADAS. Next, real-time EV monitoring and ADAS. This project focuses on building a real-time EV monitoring system using the STM32 Blue Pill microcontroller. The system continuously monitors important vehicle parameters such as vehicle speed, battery state of charge, motor temperature, vehicle range, and motor torque. It also implements ADAS features like collision detection and blind spot detection. The processed data is transmitted through UART and displayed on a live Python dashboard for easy monitoring. Next, from gaps to a unified dashboard. Modern electrical vehicles generate a large amount of real-time sensor data, making manual monitoring difficult. Important parameters such as battery condition, motor temperature, and nearby obstacles may be missed, increasing safety risks. To overcome these challenges, we developed a centralized EV dashboard that provides live vehicle monitoring, Python visualization, collision warning, blind spot detection, battery monitoring, and a fault and alarm system using UART communication. Next, project objectives. The main objective of this project is to design an EV monitoring system using STM32 Blue Pill. We interface unlock sensors through the ADC, calculate EV parameters such as speed, torque, battery SOC, and range, and implement ADAS algorithm for obstacle detection. Finally, all the information is transmitted through the UART and displayed on a Python dashboard in real time. Next, electric vehicle and ADAS features. Electric vehicles are more energy efficient, require less maintenance, and produce zero tailpipe emissions. To improve safety, we implemented advanced driver assistance system features including forward collision warning, blind spot detection, and overspeed warning. For example, a collision warning is generated when an obstacle is within 50 centimeters, while a critical alert is generated below 20 centimeters. Blind spot detection becomes active within 30 centimeters, helping the drivers avoid potential accidents. Next, system architecture. This slide shows the overall system architecture. The sensor inputs are first read by the STM32 Blue Pill through the ADC conversions. The controller processes the sensor data, calculates EV parameters, and executes the ADAS decision logic. Any alarm or faults are generated before the data is transmitted through UART1 at 115200 baud to the Python dashboard. The dashboard refreshes every 100 milliseconds, providing smooth real-time visualizations. Next, software and hardware stack. For firmware development, we used STM32 Cube IDE. PicsimLab was used to simulate the STM32 Blue Pill hardware, while Python was used to develop dashboard. Teraterm, VSP, and PySerial handle UART communication. On the hardware side, the project uses STM32 Blue Pill, 3 ultrasonic sensors and potentiometers, 4 LEDs, and a piezo buzzer. Embedded C and Python were the programming languages used throughout the project. Next, STM32 Blue Pill and GPIO mapping. This project uses STM32F103C8T6 Blue Pill microcontroller. The system clock is configured to 8 MHz and the communication is established using UART1 with a baud rate of 115200 bits per second. A 12-bit ADC is used for sensor acquisition with a range of 0 to 4095, and the operating voltage is 3.3 volts. The simulation runs at a speed of 31.25, and the Python dashboard updates every 100 milliseconds. Next, EV parameters and key equations. This slide shows the key EV parameters and equations used in the project. The dashboard monitors battery capacity, motor torque, vehicle speed, and energy consumption in different drive modes such as Eco, Normal, and Sport. Important calculations include ADC voltage, battery state of charge, estimated driving range, time to collision, and ultrasonic distance. These equations helps convert raw sensor value into meaningful vehicle information for real-time monitoring. Next, successfully implemented. The project successfully demonstrated a real-time EV dashboard with STM32 simulation, Python visualization, UART communication, collision detection, blind spot detection, and an alarm system. The main advantages are real-time monitoring, improved driver safety, low-cost implementation, and modular architecture. In the future, this system can be extended with CAN bus, GPS, IoT connectivity, AI driver assistant, and camera vision for deployment in real electric vehicles. Now let us begin the simulation of EV ADAS project. First of all, we will open the STM32 Cube IDE, where we will configure and write the code needed for this project. After the creation of our EV dash named project, we will have a .ioc file created. .ioc stand for input output configuration. Here we can configure the pins which we are needed as per our requirements. Then when we save, it will give and generate as a code that will be of name main.c, and then we will write the code needed for our project. But as the code is of too long, we will create source files and header files in which we write the codes and then call them in the main file. Then we will build the project, and during building the project, right click on the EV dash which is our project. Then there you can see build project option by which our project will be built, and before that select the project to build a binary file when the project is being built. And after building a project, when there are no errors, our binary file will be created and it will be saved in the files where we have given the path to it. Then let us see the PicsimLab. In PicsimLab, we are using the board that is Blue Pill as per our project requirement, and here we are using the peripherals are ultrasonic sensors, VT term, LEDs, and a potentiometer and a buzzer. Ultrasonic sensors are used to measure distance, which is used to calculate collision times and if there are any collisions that are going to happen and predict them. LEDs are used for closeness and if crash is going to happen and fault and alarms. And the potentiometers are used because we cannot give the input to the sensors in online, so we are using potentiometers to change them as per our requirements. And then VT term is where we can observe our output in virtual, and buzzer for alarms. Then let us upload the binary file which we have created in the STM32 Cube IDE. Open the file where the binary file is being created, then double tap on it. Then we can observe our outputs being printed like speed, SOC, torque, motor temperature, range, driving mode, acceleration, brake, and all those things. And this thing will be updated every 100 milliseconds. Let us change the value so that we can observe the changes here. Let us set up this. In the front distance ultrasonic sensor, let us decrease the distance. So as you can see, when I decrease the distance to 86, a red color LED is being on. It means there is a chance of being collision, and a fault alarm also gets here. And we can observe in the VT term output as alarm as critical. Then again, if we increase the front distance to 240, then this red LED and yellow LED will be turned off, and the alarm status in the virtual terminal will be none. Then when the left distance is below 30, then the blue LED will be on. It is suggesting that the left side collision is going to happen, and the alarm will be advisory. And when we increase the distance above 30, the blue color LED will be turned off. Same like that for right distance. When the distance is less than 26, then a green LED will be on, and in the virtual terminal we can observe the alarm as advisory. And in the potentiometers we can increase and change the accelerations. As we can see, I have decreased the acceleration, so the speed which is increasing rate will decrease. And this is brake, used to decrease the speed. We can observe the speed being decreased from 37.5 to 37.3 and still going on. And then is the SOC. SOC it stands for state of charge. And another one potentiometer is the temperature, which is of motor temperature. And when the temperature is above 80 degrees Celsius, then the fault LED will be on, saying there is something faulty in the system, and alarms will be come like motor is overheating fault. And when the temperature decreases to a normal range, then the yellow LED will be turned off, and the motor overheat will be not come. As we can observe in virtual terminal, before was motor overheating, now we can observe there is no such warning. Now we need to upload this data into our dashboard. For that we will create a dashboard using Python in VS Code. Then that file will be saved. Then by opening our command prompt as administrator, we will go to the path where our Python file is, and we will print in command prompt as py emertxe.py / port com4. Then our dashboard will be opened, which we have created. And if we have already created comms in the VSPE, then it will automatically connect. If we have not connected the VSPE, then we have to create a VSPE so that the data is being sent from one to another. For that, we will go to virtual serial port emulator, that is VSPE, their device where we can create new devices. As I have already created, my devices are being connected. So in command prompt we will go and enter the code as py/port com4. Then my dashboard will open, and if the comms are already created, then the comms will be connected. I have placed my blue pill as serial port as COM1, and I am taking the data to COM4. So we can observe here in my dashboard of which I have created here: speed, SOC, that is state of battery charge, and ADAS, the distances like front distance, left distance, right distances, and EV metrics where torque, acceleration, brake, motor temperature, alarm, fault, signal, those are here, and also a graph of speed showing here. And currently my speed is 60 and SOC is 95.8, and the speed is going to increase and SOC is going to reduce. As you can see, the speed is 62. Now then, let us change the values in PicsimLab and observe the changes that are going to happen in our EV dashboard. I am gonna change the front distance to below 170, then I will get a red alarm saying a possibility of collision is there. So let us observe if this is being displayed on dashboard. Yes, as we can see here, the distance is less than 170 and that is 158, and the alarm is critical, and so it is suggesting us to stop the car and increase the distance. So let us go to PicsimLab and increase the distance above 170. Then the red LEDs will be turned off, and we can observe in dashboard that the alarm will be turned off. As we can see, the alarm is turned off. Then let us change the left and right distances. Then we can observe that there is a chance of collision in left and right. Then let us observe here, we can see the alarm is advisory, and in the ADAS bird eye view we can see the left and right distances as 15 and 11. So we need to change the distances so that there will be no collision. As I have increased the distances, we can observe LEDs being turned off and the alarm is changed from advisory to none. Then let us change the acceleration and apply brakes. Then we can observe the speed being decreased. Let us increase the brakes to more. Then we can clearly observe the speed before was 74, now it is 73, now 72. As we can observe the speed being decreasing, and we can observe in the graph also before was 74, 73 and the graph was falling down, and the SOC is also decreasing because the battery is being in use. that is before the acceleration when it was high, the battery was being drained fastly, but now we can observe that as the torque is negative, the battery is 93.9 and it will increase by time. Now let us change it back and then increase the acceleration. Then we can observe the speed again increasing. Let us wait. As you can see, the speed is being increased again from 67 to 68, and we can observe that in the graph also, and the SOC is being drained fastly. Then let us see the alarm of temperature, and when I increase the motor temperature above 80 degrees Celsius, here a fault LED, that is yellow light, will be on, and we can observe that the motor temperature here also and a fault signal is on. So we need to decrease the temperature, and when we can observe here, when the fault is on, the torque is 0 because the motor is not in action. Then when we decrease the temperature to a normal level, then we can observe our torque being returning to normal. Let's wait. As we can see, the torque is being returned to normal. Like this, we have successfully implemented the simulation of EV ADAS project. In conclusion, this project has given me valuable hands-on experience in embedded systems, STM32 programming, sensor interfacing, UART communication, and Python dashboard development. It has strengthened both my technical knowledge and problem-solving skills. I would like to express my heartfelt gratitude to Emertxe Technologies for providing this wonderful internship opportunity. I am especially grateful to my mentor for the excellent teaching, constant guidance, patience and encouragement throughout the project. Their support played a significant role in the successful completion of this work. This internship has been an important milestone in my learning journey, and I am confident that the knowledge, guidance and practical experience gained will serve as a strong foundation for my future in embedded systems and automotive technology. Thank you once again.